the application is the stress measurement. It's well, how do we define these? Does anyone know how to define acoustoelasticity in one sentence from last time? Anurup?
Stress dependency.
Stress dependency of? Ultrasonic wave velocity, exactly. So if anyone ever asked you to just define this term, all you have to say is just, whenever you hear acoustoelasticity, you are talking about a stress dependency of ultrasonic wave velocity. So if your background is rock mechanics, that some of you are, you may think that, it all comes from preferential crack closure, etc. But the fact is, even in metals, we have acoustoelasticity. So the models that explain acoustoelasticity, they deal with it in more fundamental way. And we want to look at the formulation. So we just look at a very, very simple case. I don't know how good this is in your handouts, but we are looking at a uniaxial compression case, for example, the way you are looking at that. And imagine that, you are applying a quasi-static strain field. We use the uppercase U. And we want to see what happens if you have like P wave. So particle motion is in the same direction as the wave propagation. So you are sending a P wave in the same direction as you're applying the load. We want to see what happens to the velocity. The theories that you've seen so far, they tell you that P wave velocity is just a function of material properties, so it should not change. But the reality is that those are linear elastic theory, and we are ignoring some terms. So I don't know how the background of each of you in continuum mechanics is, so I try to make this as clear as possible, but you need to ask questions because you guys have very different backgrounds. So the way to demonstrate why we have increase or decrease in velocity when you apply quasi-static stress is to know that when you are basically looking at just second order terms, like when you are just using elastic modulus and shear modulus, you are ignoring a whole bunch of terms in the definition of energy density. What is energy density? What is energy density? Okay, so maybe I need to back off a little bit to explain this a little bit more. So energy density, so E sub V, is the energy per unit volume. So if you want to think about a simple linear elastic case, then you have sigma epsilon, and let's say it's completely linear. Energy density is nothing else but the area underneath. So it is basically, in this case, energy density is 1/2, let's say sigma epsilon, which I write it 1/2 epsilon k epsilon to have the same form as you can see there. The notation is the tensor notation. This is a slip from the previous handout. So for Chas and team who just came, we just are looking to see why we see stress-induced changes in velocity. Because when you look at linear elastic theorem, what we saw before was, okay, the velocity was square root of n over rho. But so if you are increasing the stress, why does it change? So that's kind of the question. And this doesn't happen only in rocks or in concrete or in materials with cracks. It also happens in metals. It happens in aluminum, steel, in all different materials. So there is a theory which is called the acoustoelastic theory, and I just want to show you a glimpse of it. So in the uniaxial case, if we have just everything is in one direction. If you are applying a strain field uppercase UX, and I'm shooting with a P-wave transducer from one side to the other, where the particle motion is in the direction of loading, I want to see how I can understand why would this velocity change. And if it changes, how would it change with changes of a strain? Is this clear? Now, the easiest formalism that I thought I could share with you is to look at the concept of energy density. In continuum mechanics, energy density is energy per unit volume, and you can think very easily that volume is area times length, so it's just the area under the sigma epsilon curve. Energy would be the area under force displacement curve, right? So that would be the equation. And just to give you a sense of why it looks like that, in very simple case, consider when you have sigma epsilon like that linear, if you write the area, it becomes 1/2 a strain, a stiffness, a strain. Now in tensor form, in the general case, 1/2 a strain tensor, elastic tensor, a strain tensor. It's kind of similar thing. We don't need to know all the details here. And this is not a continuum mechanics class. I cannot really teach everything right now. But just that we understand what's going on. Normally, when you write the strain in terms of displacement, we ignore these higher terms. We say, okay, when you are measuring with a transducer, the strain is so small that these higher order terms do not matter. So we just forget about them. So the strain energy, we only have these second order terms here. Now, if the other terms are important for whatever reason, then you have the third order terms. And if you go high, you can go higher and higher. I want to make sure that you understand why you hear the term third order elastic constants, why it is called third order. So second order elastic constants are the things you are very familiar with. E and G, K and mu, Lamé constant. These are called second order elastic constants because they come from the energy density, which is second order in a strain.
What is T?
It is trace. The trace of the matrix. So all the elements in the diagonal.
And normal stress, right?
A strain. U is a strain. Yeah, exactly. So let's call this like second order, so just that we remember. And if you look, the second order terms, the coefficients are bulk modulus and shear modulus. If you write them a little bit differently, you can have elastic modulus and shear modulus. But these are second order. Although you relate them to linear elastic, you think everything is linear, but it's kind of, when you go to energy, you go one order higher. So they are called second order. And maybe I can write what trace is. Doesn't really matter for the purpose of this discussion that you know that. But the trace, if you don't remember, is just the sum of the elements in the diagonal. And S here is sum over all the elements. Now, don't worry about it. You don't have to know how this is. Just look at the terms here, A, B, C. You sometimes see them written with different parameters. They may not be called A, B, C, but these are always called like third order elastic constants. Look why? Because they are related to the terms to the energy density, which are related to the third order of a strain. And we ignore the higher terms. I think in Winkler paper, for example, you saw that this is written. Whenever you look at acoustoelasticity, you see the term people are talking about third order elastic constants. Don't feel intimidated. It's not a big deal. So typically, we ignore these higher terms. We just look at the linear elastic. But now, to understand acoustoelasticity, we kind of have to look at the higher terms. Now, with this, we just need to have a few other reminders, and that is, one is sigma. You can get sigma by just derivative of the energy density with respect to a strain. You can show it, you can convince yourself by looking at this simple expression. But this just comes from mechanics. That's something we need to know. And the other thing that you know, maybe you have forgotten, but it is a wave equation. And the way that I will use it here is this expression that rho u double dot is, let's say, in one direction. I don't even want to do that. In one direction is just sigma over x. If you look at the way we derive the equation in one-dimensional case, this is wave equation. It's just E. So, it's easy. So this is wave equation. So that's all I need to show you why this is dependent. The velocity becomes dependent on a strain. Any questions so far before moving to the derivation? So now, very simple case of one-dimensional strain. Let's look at line by line. That's why I don't like to write equations, because when you look at all of them, it looks, but I wrote it here not to make any mistakes. So let's look at here. So if we have one-dimensional case, the strain tensor in this direction is just the quasi-static strain, and this is the dynamic strain. Separate them. This is a typo. So this is just a strain tensor. And then sigma is the derivative of elastic energy density with respect to a strain. Since it is the same a strain, you can use this or that, doesn't matter. And that would be the expression, without showing you why. You can derive it, of course, but this is the expression. Yes?
I'm just trying to understand. So this is in the one-dimensional case. So are we starting with capital U sub x is the initial position, and then we're straining it. So we see we're adding in that component plus lowercase u sub x. I guess I'm not following why it's a sum.
It's just with reference to this figure. So we have a situation where you have, let's say, imagine you have two transducers on both sides, P wave, and at the same time you press the sample. in one direction. Because of ultrasonic wave propagation, you have some dynamic strain inside, so that would be ux, the small. It's dynamic, normally it's smaller. But then you have quasi-static strain field, which is here. Everything is one-dimensional, so in the strain tensor, it will be just one. Everything else is zero. This is a very simple case. Please ask questions. I've tried to make this as simple as possible, but it may not be still very simple if this is the first time you see it. So that's kind of for one-dimensional case, for uniaxial case, that's kind of the strain situation. Remember that the large one is normally also larger, the quasi-static one. So that's coming from the quasi-static. And this is dynamic. And if you take this U and substitute this back in the energy density, you see it's a function of U. If you put that U in and make a derivative with respect to ux or ux, doesn't matter, U has the same relationship with respect to both, you are going to get this. So that's very interesting. You see that there is one term which is just multiplied by ux, which is the quasi-static stress. One term is just the dynamic, and one term is the coupling between the two. And that's what causes acoustoelasticity. So this term is like the coupled term. So then this is just a static stress. So it really doesn't play a role in wave propagation. The rest will be the dynamic stress. So we kind of divide this sigma into static and dynamic. And then if you put this sigma into wave equation, you will see that the relationship between U double dot and the second derivative with respect to x takes this form. So that's exactly what we are looking for. So basically, we have the static, dynamic, and just taking the dynamic, and that's nothing else but wave equation in one-dimensional case. If you substitute for the dynamic stress from the top, you will get this relationship. This is V0 squared. Now, and that's beta 1, 1. That's where it becomes important to just understand what this is. The derivation, I hope you got some understanding, or maybe you understood the whole thing. It would be even better. But you just have to see why the quasi-static strain actually comes into the play. It's just because of this coupling. So if these terms A, B, and C, they are zero, this coupling will go away. So here, if beta 1, 1 is equal to 0, look at this relationship. So then you have just wave equation, the normal relationship. Acoustoelasticity, the effect of ux, makes a change in the wave velocity. The notation is a little bit screwed up here. So this is ux squared, and this is u0 squared. And then you can, from here, you can approximate the square, you bring it to one side, and you can see that it tells you that the change of stress, the change of wave velocity in this direction with respect to the original wave velocity is proportional to the quasi-static strain. So that's where I wanted to get to, basically this relationship after all of that. look, I mean, it's not as, it's just, there are lots of terms. It's not as complicated that, and then it looks like. So we just put U inserted into energy density. We calculate the stress, and we say, okay, the dynamic stress is the part which has to be in the wave equation. And if you substitute that, you will see that the velocity here won't be constant anymore. You will have a term like that. So the dependency between the second derivative with respect to time and distance won't be just one single number anymore. It would be related to this beta, which is the acoustoelasticity coefficient. And since these changes are small, we can see that the change of velocity with respect to the reference velocity will be proportional to the strain. Between these lines, of course, there are steps that I'm jumping over just because it's not very important to go through this derivation. But at the same time, it's important to see where it is coming from. So the bottom line is if you apply a stress in one direction and you have wave velocity, the change in wave velocity is linear with respect to the strain that you're applying. So if you apply a strain, the velocity you expect to increase or decrease linearly. Now, increase and decrease is an important thing. So ux, if it is negative, meaning that we have compression, we expect the velocity to go up. So beta 1 is actually positive. That's why you have this negative there, it's built in. There are other formulations, but at the end, that's important. So acoustoelasticity theory predicts a linear relationship between velocity change, relative velocity change, and quasi-static stress. Yes? This is true for all materials if you're in the elastic region. So remember that everything is in elastic, and it's called acoustoelasticity. And what is different between different materials is this acoustoelasticity coefficient. It's really different. And then in rocks, in the very beginning, you also see this linear relationship. But then people interpret this from the macroscopic point of view. They say, okay, the reason for that is that cracks close. So basically, this is a macroscopic view of how that crack closure changes the elastic constants. That's the macroscopic view, why it is happening. That's how I see it. But in the very beginning, so it is only valid when you are in the elastic region. When you go past the elastic, everything, the whole theory falls apart. But this is not the only important thing. So try to remember a little bit of the derivation so you can kind of have a feeling about it. But I don't expect you to derive this. But yeah, please. Yes, that's that. What is very important is I call this beta 1,1. But there is also beta 1,2, for example. There is beta 1,3. And so let's say, for example, let's look at the situation where you have, this is the U, the strain tensor, and you have, let's say Ux is here, let's call it Vx. And you are still measuring with p-wave velocity, but you are applying so here you are applying the force perpendicular to the direction of the wave propagation. Everyone can see that? So it's like, okay, here I'm sending this wave, but the force is in this direction. So this beta from what you would get here would be less than beta 1,1. So the theory tells you that the largest beta that you would get is actually beta 1,1 when you have this particle motion parallel to the load. The other betas, you can do the same thing for all of this, and you can get other betas, but they will be all less than beta 1,1. And this is something that we saw last time when we were looking at the paper on the rocks a little bit. Let's go there. This one. So here, now enough with derivation. Here, what we are looking at, if you just look at the very, very beginning, you can still say that in the very beginning, acoustoelasticity is the major mechanism. So for what is happening here. And here the load is in the axis, along the axis number 3. So V33 is increasing very sharply in the beginning. And then you have 3,2 and 3,1. So here, I think Vij, maybe it's good to write this. The first one is particle motion. And the second one is the direction of propagation. And you can see that, I mean, this is not the best here, but here there is some little increase, but much smaller than that. The very beginning, when we are still in the elastic region, very, very small. And then for the other ones, it's even going down. So this you can actually predict in the very beginning with acoustoelasticity. What happens when you increase the stress? You go out of the elastic region. So in terms of, for rocks or for concrete, you start to develop macrocracks. And then last time you saw the relationship between velocity and macrocracks. So as you get more macrocracks, then the velocity is decreasing. And then this is what you are going to see. So there is kind of two mechanisms which are competing. One is here acoustoelasticity, crack closure macroscopically, and then they're competing, and then macrocracking takes over. So, any questions about this? So this is kind of showing you that. So in the beginning it's kind of linear, and then this slope becomes smaller, and then it goes down. We had acoustic emission data here, and you can very easily see, like the moment where you start seeing these changes, the number of events goes up, and then it becomes huge. So you can actually really see when macrocracking is taking over acoustoelasticity. I should have brought that figure here. These are in two different polarizations. Yeah. So that's an experiment which I showed you last time. I showed you last time this one too, but now with what we learned, again, let's look at this again. This is an experiment where we didn't measure bulk wave, we measured surface wave on the surface. This gave us the opportunity to look at how the velocity is changing at different angles with respect to the load. So to really look at every 10 degrees. I don't know if it's very clear in the picture, but this was a huge loading frame, and the specimen is 3 feet by 1.5 feet by 2 feet. It's a huge piece of material. So at the end, when it exploded, it was dangerous. So we couldn't be near the experiment. So we used a laser vibrometer, like a scanning laser vibrometer. Actuator in the middle, and then a laser vibrometer which was automatically measuring the surface reflection. So what we were looking for was surface wave. In the very beginning, if we normalize everything, of course we would get a circle with diameter 1. It's normalized. And then you see when you increase the load at the location where you are parallel to the load, you start to see increase in velocity. And it's kind of very, very nice and smooth. It's every 10 degrees curve. And as you increase the velocity, the load, it still increases. And you can very easily see what I told you about direction dependency, because here is maximum, and then as you go here, it becomes minimum. And well, of course, concrete is very heterogeneous, so you don't get a perfect ellipse, but it is real data, so this is what we got. And then between 50 and 75, that's when we approach this plateau, where microcracks are developing and there are two competing mechanisms. So you kind of see that they start to overlap. And just before failure, everything shrinks back. So in all directions, microcracking is definitely dominant, and it all goes down. So it kind of, I think it shows very well how stress creates anisotropy in material, and it is measurable with ultrasonic waves. And here we are using surface waves, which is you just have two transducers on the surface, so you don't even need to look somewhere else, and you can really nicely see what's going on here. And as another application, last time I showed you this situation where in the US, apparently people years ago decided that it's good to have continuously welded railways. But the problem with that is that thermal stress develops, and then you get this sort of buckling all of a sudden, and that derails trains. So it's a big problem. One way to measure stress, there is actually no way to measure stress. It's a very hard thing to measure. So one method that people use or have developed is to measure ultrasonic wave velocity. So this is also real data. So you can see this linear relationship between delta V over V. This is uniaxial, so it's very nice. And you see as you increase the stress, delta V over V is increasing very linearly. But the values are small, so you are in the acoustoelastic regime. I also showed you this slide last time, but now maybe you understand this a little bit better. It looks old because this is kind of the first reference I've seen in this domain. And that's a very, I think, a smart way of doing it. So people also realize that this is not truly uniaxial. So in the other direction, you also have some stresses. So one method was to use two polarization. These are shear wave probes. One polarized in this direction. That is what gives you TL. And the other one is polarized perpendicular to the rail axis.
Something about the rails, why they? Like you said, it's because they're too long.
I said it's too long.
Yeah, you said it's like continuous, and
Yeah,
that's why.
but that's in place. It's in service.
Yeah.
To cut it?
Yeah, and then like going to that, like you would do.
But that's
in an
completely destructive. So how often do they have to do? And then the whole thing becomes you're suggesting that they go back to the network and cut everything?
Yeah, rather than pay for expensive sensors.
They're not very expensive. This is now they have trucks that they drive over. I'm not a railway engineer, but I don't think that's feasible to cut every day.
Okay.
I don't think, if it was feasible, they would do it. It wouldn't be a big problem. Even this year, there was an RFP looking for. It seems that it's a big problem. I don't know. It looks to me that there is a lot of railway to go and cut. Maybe there will be some
It's
other
not,
issues.
that would take longer than
Right. I don't know. I mean, this is not something that I would do. I know that one of my students who works now for Deutsche Bahn, I mean, they do this on a normal, on a regular basis. It's not expensive. It's apparently it is worth it. There is a reason to do that. But I don't know the reason. You should ask someone who's a railway engineer. But the way they look at it is to have these two polarizations. This is kind of very smart because one polarization is very sensitive to the stress in this direction, and the other polarization is kind of not sensitive to this stress. And if you look here, the stress, the area underneath is 0. So it kind of cancels each other out if you have this other polarization. So it's a very smart way to do that. And if you measure in both directions, you can actually calculate a stress, absolute value of a stress in the ray. It seems that in the field, that's not always the case. So a lot of times they use what I showed you in the beginning. They use transducers on the side, and then they have some baseline measurement, and then they go from there, from the linear relationship. So that's kind of what you have to know. So with that, last time also kind of, I didn't want to show you the acoustoelasticity, now you know why. We kind of decided to summarize what we learned about how we can use the resonance. We had talked about impact echo, if you remember, looking at thickness resonance, looking at Q factor, and then the relationship between velocity and crack density. We saw that, if you know the velocity change, there are ways you can get crack density and attenuation, etc. And to that, we want to add maybe a few things about acoustoelasticity, more in terms of applications. So try to just think about the things we talked so far in the class and write down a few sentences what it is and why do you think it can be useful. And then it's not a thing. It's just a small thing. I thought it would be good to think about So I think the important things are stress. Just that we all remember, this is a stress dependency. And I think there are two important things, really. One is to remember that this theory predicts. Now we use negative, it's fine, we can use negative here. A linear relationship between change of velocity and a strain, which can be used to measure stress. I've uploaded the note